Good morning. This is class 6 on our unit for magnetic properties of solids. Today we are going to discuss about transition region between domains. Now what is meant by a block wall? A block wall in a crystal is a transition layer that separates adjacent regions or domains magnetized in different directions. See, we have already discussed about domains. See, this is a domain. This is another domain inside which you will have magnetic moments oriented in different directions. Okay. Now suppose that these two domains are separated by a transition layer. Okay, now this transition layer that separates adjacent domains magnetized in different directions is called as a block wall. Okay, the entire change in spin direction between domains does not occur in one discontinuous jump across a single atomic plane but takes place in a gradual way over many atomic planes. The meaning is this one, that is we said domains are having different spin directions. Okay, spin directions between domains will be different. It will vary from one domain to another, and that change in the spin direction between domains will not occur in a single jump. Instead, that change will occur only gradually over many atomic planes. Okay, now the exchange energy is lower when the change is distributed over many spins. Now, this behavior can be understood by interpreting the Heisenberg equation, which we have already discussed. U is equal to minus 2j Si dot Sj. Si dot Sj means Si Sj cos phi. Okay, cos psi, because dot product means it is cos function. Okay, so Si dot Sj means Si Sj cos psi. So remember there exists a cos psi there. Now suppose that you replace that cos by psi by 1 minus half psi square, then omega or Wex is given by j s square psi square is the exchange energy between two spins making a small angle psi with each other. Here j is the exchange integral, s is the spin quantum number, and Wex is the energy for parallel spins. Okay. Now, if the total change of pi occurs in n equal steps, suppose that there are n equal steps and the total change that occurs during these n equal steps is pi, then the angle between neighboring spins is given by pi by n. At the same time, exchange energy per pair of neighboring atoms is given by Wex is equal to j s square pi by n the whole square. Therefore, total exchange energy of n plus 1 atom will be n Wex j s square pi square by n. Okay. Wex is only for exchange energy for nth atom. If it is in the case of n plus atoms, n plus 1 atoms, then Wex has to be multiplied with the n. So, n Wex is equal to j s square pi square by n. That is the expression for total exchange energy of a line of n plus 1 atoms. Here, just remember, there is no derivation available about all these things. You will just have to study the expressions only. Okay. Now here we have talked about a block wall, right? Now the thickness of this block wall will go on increasing without any limit. Okay, and sometimes by the action of anisotropy energy, sometimes there will be a limit to the thickness of this wall, or there will be a limit to the width of this block wall. Now the spins contained within the wall are largely directed away from the axis of EC magnetization. Axis of EC magnetization we have discussed in our earlier classes, right? So the spins which are contained within the block wall is directed away from the axis of EC magnetization. So definitely an anisotropy energy will be associated with the wall, and that anisotropy energy will be proportional to the thickness of the wall. Consider one such wall, or consider a block wall parallel to the cube face of a simple cubic lattice and separating domains magnetized in opposite direction. Now to determine the number n of atomic planes contained within the wall, the energy per unit area of the wall is considered as sum of contributions from exchange and anisotropy energy. That is contribution from exchange energy, contribution from anisotropy energy. Okay. Now exchange energy, we know it is already given by equation 1 for each line of atoms normal to the plane of wall. Now there are 1 by a square such planes per unit area. Suppose that there is 1 by a square lines per unit area where a is the lattice constant. Then exchange energy sigma Ex is given by the expression pi square j s square by n a square. Now anisotropy energy is of the order of anisotropy constant times the thickness. So that is anisotropy constant n times the thickness a. Okay, or we can write anisotropy energy sigma anisotropic equal to kNa. So we can write this expression for uh, the energy per unit area of the wall sigma omega as this one sigma exchange energies expression, this one, and anisotropy energies expression. Okay, now this particular term, that is this energy per unit area of the wall, that is sigma w, is minimum with respect to n when its derivative with respect to n is 0. That is when dou sigma or w by dou n equal to 0. That is when this particular term is equal to 0. From that term we can find the expression for n as n equal to root of pi square j square by ka. Okay, ka cube. Now here they have given a value, just an example uh, for iron. No need of mentioning that. Okay, so up to this much is enough. Next is origin of domains. Now this domain structure is a natural consequence of various contributions to energy like exchange energy, anisotropy energy, and magnetic energy in the case of a ferromagnetic material. Now, the direct evidence for the existence of domains is given by photomicrographs of domain boundaries, which is obtained by a technique of magnetic powder patterns and also by optical studies. Okay, using Faraday rotation. The powder pattern method was developed by F. Bitter, and it consists of placing a drop of colloidal suspension of finely divided ferromagnetic material such as magnetite on the surface of a ferromagnetic crystal. Then what happens to the colloidal particles? The colloidal particles in the suspension concentrate strongly about the boundaries between domains where strong local magnetic field exists, which attract the magnetic particles. Now the discovery of transparent ferromagnetic compounds has encouraged the use of optical rotation for domain studies. So these are all just theories, you can just read through. Now here the origin of domains is again can be also more clearly understood by studying or by considering the structures shown in the figure, each representing a cross section through a ferromagnetic single crystal. So in figure A, you can see a single domain. As a consequence of magnetic poles formed on the surface of crystal, this configuration given in figure A will have high value of magnetic energy. Okay, and they have given that value of magnetic energy there. Just write that value 10 raised to 6 earth per centimeter cube. The rest you can skip. Now what about figure B? In figure B, magnetic energy is found to be reduced by about 1/2 by dividing the crystal into two domains magnetized in opposite direction. See, arrows, they are in opposite direction, right? Now what about figure C? In figure C, there are n number of domains and the magnetic energy is reduced to approximately 1 by n of the magnetic energy of A. Okay, why? Because of the reduced spatial extension of the field. Now again you have got two more figures, figure D and D. In domain arrangement, in that is in figure D and D, magnetic energy is 0 because in these two cases boundaries of triangular prism domains near the end faces of the crystal make an angle 45 degree with the magnetization in the rectangle domain and the magnetization in the domains of closure. The component of magnetization normal to the boundary is continuous across the boundary and there is no magnetic field associated with the magnetization. So here what you have to write is just draw these two figures and write as per consider the domain arrangement in figure D and T. There the component of magnetization normal to the boundary is continuous across the boundary and there is no magnetic field associated with magnetization. These sentences you can skip, only write this sentence what I have marked. Okay. So here this session you can go through, that is write about each figure, what is seen in figure A, figure B, figure C, and then in figure D and D. Now the flux circuit is completed within the crystal and it will give rise to domain of closure. This figure is called domain of closure, and here the surface domains is found to be complete as which is shown in the figure. Now a paragraph about domain structure, that is domain structure always has its origin in the possibility of lowering the energy of a system by going from a saturated configuration with high magnetic energy to a domain configuration with low energy. Okay, this sentence we can mention. What is meant by a domain structure? That is, a domain structure will always originate from the possibility of lowering the energy of the system. A domain structure always lower the energy of the system. How? That is, it undergoes a transition from a saturated configuration to domain configuration. Saturated configuration will have high magnetic energy, whereas a domain configuration will have low energy. So it goes a transition from high energy saturation configuration to low energy domain configuration. That is the peculiarity of a domain structure. Okay. So here transition region between domains, if here there are only expressions, so you need to learn only those expressions. There is no derivations are not available, so if possible you can learn it, but you can skip this example, no need of mentioning this example. Then about origin of domains, it is just theory, you can note the important points, but here you have to note these points, that is write one or two sentences regarding each figure, figure A, B, C, finally D and D. Regarding D and D you need to write only this. Okay. Then finally about the significance of domain structure. Okay, thank you.